Welcome back to Everything NCEA. Today is a huge lesson because we're starting thermochemistry. This is what the lesson plan that I'm going to be teaching looks like, or going through, not teaching. But yeah, this will be what I'll be going through with today, starting with electron configuration of subshells, s.p.d notation, and electron energy levels. So we'll start with a little level 2 recap for those that didn't do chemistry in level 2, and for those that did, just a little refresher. So electrons in atoms and ions occupy shells, and each shell has a specific number of spaces available. That's a good way to think about it. Once one of the inner shells is full, further electrons will then need to occupy a shell further from the nucleus. This can also be described as the principal energy level, and electrons within that shell have similar energy. So electrons inside the second shell will have similar energy. That's what that means. In level 2, and previous chemistry at high school, you would have thought about atoms and electrons, with the first shell holding 2, the second shell holding 8, the third shell holding 18, and so on. Whereas in reality, and in level 3, these are further broken down into subshells and sublevels. These different subshells represent a slightly different energy level within that overall energy level. And these subshells contain atomic orbitals that hold 2 electrons each, and with each subsequent subshell, and the subshells are named s.p.d.f, there are more orbitals. So an example, an s subshell has 1 orbital, a p has 3, a d has 5, and so on. That'll become much more clear later on. So we'll have a look at the platinum ion there. We have the first energy level, which has a 1s subshell. The second energy level, which has a 2s and a 2p. The third energy level has 3s, 3p, 3d. Fourth has that, and so on. Oh, I'll just go back quickly. So that's where the chemistry and the understanding gets built on in level 3. The first shell has 1 subshell, and this is the s subshell, which has 1 orbital that can hold 2 electrons. The second shell has 1 s subshell and 1 p subshell. The s shell has 1 orbital that can hold 2 electrons, and then the p has 3 orbitals holding 2 electrons each. And then you got the third shell, which has a s, a p, and a d subshell. Again, the s subshell has 1 orbital that can hold 2 electrons. The p has 3 orbitals holding 2 each, and the d has 5 orbitals, which also hold 2 each. A lot of information. It makes sense later on. So I'd implore you to pause and try and give this a go first. But what this is, it's a little quick graphical representation of these subshells. So I'll put a little marker here. You've got the first energy level, which has a 1s subshell, which has 1 orbital and holds 2 electrons. Then the second energy level has a 2s and a 2p. The 2s has 1 orbital, the 2p has 3, and they each hold 2 electrons. And so in previous years of chemistry, you would have thought about the first electron shell holding 2, which is what this is here. And then the second electron shell holding 8, and that's what this is here. It's just this is broken down into 2 electrons here and 6 electrons here. There's still 8 overall, but you're just looking at a bit more in-depth view. Now the third energy level is a little more tricky. To start it off, it's got a 3s and a 3p, same as the 2. But this little line leading out here, we'll leave that for now, and we'll talk about the 4. The 4 has a 4s, a 4p, and it goes on, but in level 3, the highest you'll ever really go is a 4s, potentially a 4p, but that's extremely rare. Then the last one here is a 3d. The reason the 3d is above the 4s is because due to factors which we'll learn later on, so I won't go too much into it now, but the reason it's above is basically because the 3d orbital is further away from the nucleus than the 4s. So electrons are we'll go into that in future lessons, but looking at it this way will help us with our next bit, which is how to write out this notation for just some simple achieved questions in the exam. So yeah, here we'll be writing out the electron configurations in s.p.d notation, which sounds tricky, but it's not. So the correct notation is over here with the 1s shell housing 2 electrons, the 2s housing 2 electrons, the 2p can hold 6, the 3s can hold 2, the 3p can hold 6, and so on. This number in the top right above the letters, that's how many electrons are in that subshell. So again, pause if you want to give it a go. I'll let you pause now. But we'll start with lithium. The first step for writing out the notation is count how many electrons it has. Lithium has 3. So you would then write out the notation and making sure that these little superscript numbers add to 3, because this basically means that it's got one s subshell which holds 2 electrons and one 2s subshell which holds 1 electron, and when you add these together that equals the 3 electrons. And that's basically how you write it out. It's not hard, it's just adding up numbers and remembering which order to write these in, with a special rule that the 4s over here has to go before the 3d when we're writing out our notations. That's just an important rule to know. Then how many electrons does neon have? That's 10. So we would write it out with 2 plus 2 being 4, 4 plus 6 being 10. So we know that that's correct. That's how we double check. And it goes 1s, 2s, 2p. Chlorine has 17 electrons, so we make sure that that equals 17. That's how we'd write chlorine. And then if you didn't give these 3 a go, give titanium a go, knowing that you've got this notation up here. Give it a go, pause it, give it a go, because I'm going to go through it now. First step, count the electrons, 22. Second step, write out the correct notation, and then just counting up to 22 with the electron shells. So 2, 4, 10, 12, 18, 20, 22. Remembering that the 4s comes before the 3d. It's a stickler to remember, but you have to remember it. This is the notation that I prefer writing in. You can also write it in, oh, that box is funky. You can also write it in like this, which is basically you write the noble gas that comes before the atom, and then the subsequent electrons that the noble gas doesn't have. So for lithium, the noble gas before it's helium, which is the 1s. So helium, if we write, would be 1s2, so that's there. And then helium doesn't have this 2s1 and lithium does. Neon, the one before is helium. You wouldn't just write neon because the examiners would just, they wouldn't accept it because you're just writing any. Before chlorine is neon. And then the extra bits that neon doesn't have is this bit here. And then after the one before titanium is argon, and so on. I don't like that. I find it more confusing, but you can use it if you want. Ask your teachers about that one. If they use it, I'll be using the one I taught first throughout this. Now, the filling of the orbitals can also be represented graphically. So boron has 5 electrons, so each of these arrows is representing an electron. And so you've got the 1s subshell, which holds 2, the 2s, which holds 2, the 2p, which holds 6, but because boron's only got 5 electrons, there's only 1 electron in there. And then same with sulfur, each of them arrows is a electron. But when we're writing graphically, there are rules we have to follow. The rules sound complex because they've got funky scientist names that go with them, but they're the most simple rules you'll learn in thermochemistry. They are super simple. Don't get stressed out by them. You've got, I always butcher this, Aufbau's principle, or the occupation of orbitals rule. And this is basically electrons will fill orbitals in a way that minimizes the energy of an atom. For this to occur, electrons will fill the principal energy levels in order of their increasing energy, which simply just means it goes 1, then 2, then 3, then 4. Or in other words, a subshell must be filled completely before moving to the next level. So yeah, you got to fill the 1s2 before you go to the 2s2, you got to do the 2s2 before the 2p, and so on. And that correct order looks like this. The next rule is Pauli's exclusion principle. So for each orbital can hold a maximum of 2 electrons, which you can see here. So do a quick little draw. This is 1 orbital, 2 orbitals, and they can each hold 2 electrons, no more. No, and the arrow's direction represents the electron's spin. You don't need to know too much about that, just understand that it's the spin. No 2 paired electrons in an orbital will spin in the same direction. So you have 1 arrow going down like that and 1 arrow going up like that. It cannot look like this, 2 up, because electrons will never form like that. It'll always be 1 down, 1 up. So that's always how you write it. So yeah, simple rule, just remember to write 1 down, 1 up. That's easy. And then you've got Hund's rule, which is the last rule for assigning electron orbitals, which is simply every orbital in a subshell is singly occupied with 1 electron before any orbital is doubly occupied, and all electrons in singly occupied orbitals have the same spin. So when we look at the representation of carbons here, each electrons, you've got an up and a down arrow, so that's correct. But instead of going 1 down here, 1 up here, you would fill it out with 2 going up. So you make sure that each of these, this one here, and this one here, you make sure that each of them has 1 electron before you start adding the second electron in. So if you're going to go to the atom after carbon, it'd be that, and then you would start filling it in this way. But always make sure they're singly filled first. Another simple rule, just make sure that you go single before double. That's how I remember it. Now in chemistry, we love our exceptions. There are only 2 for thermochemistry level 3, and they are the elements chromium and copper, and they do not follow the rules specifically. We'll have a look at this here. You have copper. We'll go back. This is the correct way of doing it. And the keen-eyed people watching would go, why wouldn't you fill this 4s first? Why? You would think from the previous rules that you'd fill that 4s first and there wouldn't be 1 there. That's what you'd think. Whereas, yeah, that's the incorrect way of doing it. The correct way is doing the 3D before the 4s. Same with chromium. This is the correct way. You would think, why isn't it this? Why don't you fill the 4s before doing the 3D? Whereas this is the correct way. And that is because there is stability in having a complete set of filled or half-filled orbitals. So the atom has more stability with these being completely full or half full than if it wasn't like that. So chromium has 5 3D electrons and only 1 electron in the 4s orbital, because that makes the atom more stable. And same for copper, because having a completely full 3D orbital is the more stable than having a partially filled 3D orbital. They're the only 2 exceptions. Just memorize them too, in case they come up in your exam at the end of the year. And that's just going through it again. This is because there's greater stability in having a complete set of filled or half-filled orbitals instead of having some full and some mixed. So now we're nearly done. We've got the electron configurations of ions, and this is how we do s.p.d notation for ions, which differs it doesn't differ from atoms, to be fair. It's just you've got to remember one additional thing. As we already know, ions have a different number of electrons than protons in the nucleus. This means that when we write the electron configuration of the ion, we first have to make sure we calculate the total number of electrons that the ion has, and then subsequently use the s.p.d notation, making sure to account for the electrons we've counted. To make that simpler, for each negative charge on the ion, I'll quickly write this on the side. If the atom has a negative charge, ion negative, you add the same number of electrons. For each negative charge on the ion, you add the same number of electrons on top of the element's s.p.d notation. That's a little tricky. So if it was O2 minus, you would add 2 more electrons to oxygen's s.p.d notation. And we will have a look at that in the example there. So using this example of oxygen has a 2 minus charge, which means it has, there you go, oxygen atom has 8 electrons, which looks like that. The oxygen ion has 10 electrons because it gains 2. So the ion becomes more stable, which we should have learned, and if you haven't, that's why. Which means this ion now has a total of 10 electrons, not 8. So when doing your s.p.d notation, you need to make sure to write 10 electrons, not 8. So you can see the small difference there. Instead of having the 4, you got the 6. Because 2 plus 2 plus 6 is 10 electrons. Whereas 2 plus 2 plus 4 is 8. So yeah, for ions, if there's a negative charge, you add electrons. If there's a positive charge, you take electrons away. We'll do a quick bit of practice with that, just to get it down. So the nickel atom has 28 electrons, which the s.p.d notation looks like that. Whereas the nickel ion has 26 electrons. So because there is this 2 plus charge, you take 2 electrons away. So from 28 to 26, you've taken 2 away, with the notation looking like this. Now, what you have to remember here, which is just a quick rule which is sometimes often not taught well, the electrons in the 4s orbital are lost before the 3d electrons. So you lose these electrons here, as you can see they're not there, before you take anything away from the 3d. That is because the 4s subshell is in the 4th energy level, so there are less attractive forces on it, so the electrons are easier to be taken away by another ion when they form ionic bonds, which another lesson will cover that. But yeah, you take away from the 4s subshell first, and then if it was a 3 plus charge, you would then take 1 away from the 3d. With phosphorus, how many electrons does it have? It has, I'm still drawing, it has, so yeah, the 4s orbitals are lost before the 3d. It has 15 electrons, with the notation looking like that. So because it's got a 3 minus charge, do you think we would have more electrons or less electrons? The answer being we would have 3 more electrons, with that correct notation looking like that, as this notation has 18 electrons, whereas this only has 15. And yeah, that's basically s.p.d notation. quick, easy. We'll do one more on colored. We'll do a little bit on colored compounds at the end, because it's something that it very rarely comes up, but on the off chance it does, it's useful to know because a lot of schools just overlook it. And I know in recent years there has been a little bit where knowing colored compounds just makes questions easier. So I'll go through it, but that right there is really good fundamental knowledge for the rest of this exam learning. In 20 minutes, we've gone through a solid chunk of what the exam is. Using these notations and understanding these notations and the electron orbitals is vital in what comes next, and that's why we've learnt it first. But we'll finish on colored compounds. So something interesting to keep in mind is that transition metals can form colored compounds if they have singularly occupied d orbitals. The electrons absorb a specific wavelength of visible light spectrum, and this energy absorbs ends up promoting the electron into a higher orbital energy level. We'll have a little look at something down here in a minute. So the wavelengths that don't get absorbed are then reflected, which is what gives the compounds their distinctive colors. The metal ions of ionic compounds where the 3D subshell is either completely full or empty have a white appearance in the solid state. That's a little wordy and a little hard. What it basically means is but we'll have a look at copper. You got Cu2 plus and Cu plus. Now, which one of these would be colorful? Have a guess. That's probably enough time for a guess. The answer is Cu2 plus, and that would look blue, but you don't need to know why, it just would be blue. And that's basically because if one of the transition metals has a full 3D subshell, or half full, and half full would be that, one in each of them. If it has a full subshell, it will be a white substance. If it's partially full, as you can see, this has got 1 down, 2 down, 3 down, 4 down, but it's missing this one, so it's partially full, means it's colored. And that's just a little bit of extra information on colored compounds and why the compounds are colored. Understanding the electron spins and the notation like that helps you understand why they become colored, because the wavelengths that don't get absorbed are then reflected, which is then what gives the copper its blue color. And then if the subshell was completely full, all of the wavelengths would be reflected, so it would just look white. Whereas Cu2 plus, there's the blue wavelength specifically gets reflected, whereas the others get absorbed because it's missing that electron there. And that is basically why colored compounds are colored compounds. So yeah, the partially filled 3D orbital absorbs some wavelengths of light. The transmitted light appears colored. The electron configuration is blah blah blah. There are no partially filled. So yeah, just because it's missing that little electron there means it is a colored compound. If it is full, it is a white compound. And that's the start of thermochemistry. Hope that helped. Ask me through emails or your teachers through school any questions. And I'll be here in a couple weeks' time with the next lesson of thermochem.